So far in this course, we have talked about the basics of C++. Soon we will start applying what we've learned to numerical methods, such as solving nonlinear algebraic equations or ordinary differential equations, or doing numerical integration, numerical differentiation, and so on. And we will discuss numerical solution of ordinary differential equations in more detail, but before we discuss numerical solution, let's first discuss ordinary differential equations in general. Suppose that we have a variable y of t that depends on some parameter t, which could be time, or it could be some other parameter like distance or something else. Then it may be natural to specify how y changes with respect to t using a differential equation. This is a first order differential equation, dy by dt equals some function f of y and t. Differential equations are widely used in physics, chemistry, biology, finance, mathematics, and many other areas. In this example, t is referred to as the independent variable, and y is the dependent variable. This is a first order differential equation because it only involves the first derivative here, and there is no second or third or higher order derivative present in the equation. It's also an ordinary differential equation because there's only one independent variable t, and so y is only a function of t, so we only have to calculate an ordinary derivative here of y with respect to t. If y depending on more variables like t and x and z and so on, then we would have partial derivatives showing up here, and this would be a partial differential equation. But we will not discuss this case for now. We will focus on ordinary differential equations. The independent variable, like I said before, it doesn't have to be time. It could be distance or something else, and we will see cases of that later. We can have differential equations with more than one independent variable, such as a quantity that varies in space and time, and as I just mentioned, this would need partial differential equations, but we will only cover ordinary differential equations in this video. A solution of the differential equation is a differentiable function y of t, such that when I differentiate y of t, I get f of y of t and t for t in some interval, let's say from t1 to t2. In general, there is a whole family of solutions that may depend on some constant parameter. We can then specify an initial condition if this is an initial value problem. So if we specify an initial condition that at initial time t0, y of t0 equals some number y0, and then we can require that our solution satisfies this initial condition, then that will fix the arbitrary constants in the solution, and then we can get a unique solution. So for example, suppose that our differential equation has the form dy by dt equals ry, where r is some constant. This is one of the simplest cases we can get. This is a linear differential equation of first order, and we know very well the solution to that differential equation. it's simply an exponential, c times e to the rt, where c is a constant. So indeed, if we plug in this solution to this differential equation, we get that dy by dt equals rc e to the rt, but c e to the rt is just ry. So this differential equation is satisfied. So for any such y of t, we have a solution to this ordinary differential equation. So the constant c is arbitrary at the moment. It can be any constant number. We can plot the solution, y of t, as a function of t, and of course it's going to be an exponential function, so we see this exponential growth of y with respect to t. And let's suppose that our initial data is taken at some time t0, and let's look at the effect of changing the constant c. What happens is that changing c will simply shift this function, this plot, up or down. So if I increase c, it will go up. If I decrease c, it will go down. So it should be clear that there is only one specific value of c that leads to an initial y that is equal to y0. So there's only one of these solutions that satisfies the initial data, that y0 equals y of t0. So by specifying this initial condition, we are fixing the value of c, and we are fixing the solution. Okay, so this was the case, the simplest case, where we have an ordinary differential equation with only one variable. We will also encounter cases where we have multiple dependent variables. For example, we can have some unknowns y1, y2, y3, and so on, up to some ym. And each of those is a differential equation. dy1 by dt equals f1, dy2 by dt equals f2, and so on. And each of those functions, f1, f2, and so on, depend on all the other variables, which are called dependent variables, y1, y2, and so on, and may also depend explicitly on t. And again, because we only have first order derivatives with respect to t showing up, this is still a first order system of ordinary differential equations. The only difference is that now it's a system, whereas before it was one ordinary differential equation. Now we have a system of ODEs. The numerical methods that we're going to cover work very well in this case. They are optimized for a first order system of differential equations. If you have a second order system, there's a straightforward way to reduce it to a first order system, which we will discuss later. So in this case, we have an initial value problem which specifies a value for each yi at time t0. So at time t0 we have that y1 of t0 equals y1, comma 0, and then y2 of t0 equals y2, comma 0, and so on. So this is a set of initial conditions for each of the dependent variables. We can think of these dependent variables as components of a big vector y. So each component of the vector has an initial condition. Now, as I said before, we can also handle second order differential equations. This is a second order ODE because we have both first and second order derivatives showing up in this ODE. in this ordinary differential equation. Now, this is still an ordinary differential equation because it still has just one independent variable, t. So the function y is only dependent on t. It does not depend on other quantities. So it's still an ODE, but it's just second order. Now, there are methods that can solve second order ODEs or PDEs directly. But for now, we will focus on methods that can solve first order ODEs directly. So for that reason, let's see how we can reduce a second order ODE to a first order ODE, and then apply first order methods that we will learn later. So if I want to reduce a second order ODE to a first order ODE, all I have to do is put dy by dt equal to z. And then the derivative, the second derivative, d squared y by dt squared, will be equal to the derivative of this equation. So it will be dz by dt. So if I do that, then I get a system of two equations, or two ODEs. The first ODE is this definition here, this first equation. So dy by dt equals z. That is my first equation. The second equation is what I get for dz by dt by expressing the second order time derivative from the ODE itself. So here we have the second order derivative. So d squared y by dt squared will become dz by dt. And then I can take this term to the other side, and it will become minus g times z. So indeed we have here minus g times z and this f term. So, and that's the second order time derivative with respect to y, which is now reduced to a first order derivative with respect to z. So now our second order ODE has been reduced to a first order system of ODEs. So the price we pay for reducing the order of the system is that now we have more equations to deal with. Instead of one equation, now we have two. However, the methods the numerical methods we're going to describe, they can be more easily applied to this kind of case of first order systems, because I can express now these ODEs as integral equations and then use numerical integration to evolve them. Okay, so let's discuss some basic ways for numerically solving such differential equations. So let's consider again the first order system, or the first order ODE dy by dt equals f of y and t, and with some initial condition y of t0 equals y0. Now, the true solution, y of t, is going to be some continuous curve on the plane y of t against versus t. And we'll have some initial data here. At time t0, y is equal to y0. When we try to solve this problem numerically, we're typically going to form a grid of points in the variable t. So let's suppose that we are evaluating y at a set of equally spaced points, t0, t1, t2, and so on up to, let's say, tn. The distance between these points is the step size, which here we call it h, or you might call it delta t. That is going to be equal to tn minus t0 divided by n, the number of spaces. The simplest method of solving such a system is the Euler method. Starting from the value y equals y0 at time t equals t0, we can extrapolate to the next grid point at time t equals t1 by approximating the curve with a straight line whose slope is dy by dt at t0 equals f of y0 and t0. So if the slope is constant, then I can simply say that delta y equals f times delta t, or in other words, y at I plus 1 minus y at I. So the difference delta y is the difference between y at I plus 1 and yi. That will be equal to delta t, or h, times f. So here I'm using hat to denote the estimate, the numerical estimate of y at ti. In the future, we're going to drop the hat and just use yi to denote our numerical estimate for y at ti. So, in other words, we take the tangent line at ti and extend it to ti plus 1. Another way to look at this is to look at the Taylor expansion. So, a Taylor series expansion of y of t around t equals t0 is y at t0 plus h equals y at t0 plus h times the derivative dy by dt at t0 plus h squared divided by 2 factorial times the second derivative of y with respect to t at t0 plus h cubed divided by 3 factorial times the third derivative, and so on. So if we look at this, then truncating the Taylor expansion here is equivalent to the Euler method. So basically I'm calculating the function at y equals at time t1, which is t0 plus h, based on the value of y at t0 plus h times the derivative dy by dt at t0, and dy by dt at t0 is of course equal to f because of the differential equation dy by dt equals f here. So we already know the derivative with respect to t at any time t, so we can evaluate it at time t0. So if we do that, then we just need the value of y at t0 and the value of f at t0, and we can use those to approximate the value of y at the next point, t1, which is t0 plus h. Okay, so it's clear that the Euler method consists of ignoring the quadratic terms in h. So we're only keeping terms that are linear in h, where h is the time step. Sometimes we may denote this by delta t. If y of t is a smooth function, then this approximation will be convergent. So it will be close for small enough h. So as we decrease the time step h, then this approximation will get better and better. But notice that if I use this kind of time stepping to go from y of t0 to y of t1, which is this expression, then this y of t1 is approximate. And then I can use the same procedure to go from y of t1 to y of t2. Again, I have another approximation, and so on. So I have a sequence of approximations in each time step. So you may see that while the blue smooth solution is this curve here. Each time I do one time step, I may drift a little bit away from the exact solution, and then a bit further away and a bit further away. So in the end, these numerical errors accumulate, and my numerical approximation may not coincide exactly with the exact solution. But the hope is that as I decrease h, then this red numerical curve will start getting closer and closer to the blue curve. But also, if we use higher order methods that are going to be more accurate, these will approximate the exact solution much better. And we will discuss methods for how to do that in the next lectures. But for now, we will focus on the Euler method on this video, just to show how this works in C++. And then in future videos, we will discuss how to improve this approximation. And we will discuss higher order methods like Runge-Kutta methods. But we will also discuss symplectic methods or time-symmetric methods that preserve energy, and they have better stability properties and better accuracy properties, such as the Hermite rule and so on. So there will be more accurate methods discussed in future lectures, but we'll just focus on the Euler method in this video just for the sake of learning how to implement it in C++. Okay, so as I said, with a smaller step size h, we can estimate the true or the exact solution a bit more accurately. So the more h decreases, the better the approximation is. Okay, so this discussion was again for one single ODE. The same method can be applied to a system of ODEs. So let's go back to the case of a 2x2 system. So we have two variables, y1 and y2, and two equations for those variables, as well as two initial conditions. To approximate this system numerically, again, we can do what we did before with the Euler method. We can write delta y1 equals delta t times f, approximating f as constant, and then delta y2 equals delta t times f. Now delta t is equal to h, and delta y1 is y1 at t2 minus y1 at t1, and we can bring y1 of t1 to the other side, and the same for the second equation. So this is the stepping that we get if we do that. Now here, of course, instead of saying t2 and t1, I have written t at I plus 1 and t at I. And the same here. This is time I plus 1, and this is a time I. So here y1 comma I plus 1 is basically simply the estimate of y1 at ti, and so on. And then the delta t, the time step, is h, and the function f1 depends on all the variables y1 and y2 as evaluated at ti, as well as the time ti explicitly. So sometimes we may have an explicit dependence of on time. Sometimes this dependence may not be there. It may just depend on the values of y. So that depends on the problem. Okay, so now we have a simple scheme to iterate. So we can start from I equals 0 at time 0, and then go to t1, and then go to t2 using the same equations. You go to t3 using the same equations. So we can put this inside a for loop and time step all of the way and evolve all the way from t0 up to a final time tn. So this is going to be pretty straightforward to implement, and we will show how later. Okay, so of course this method is approximate and it will have a numerical error. For a single step of size h, the Euler method has an error that's of magnitude or of order h squared. So when we say that the order of the error is h squared, it means that if I decrease h by a factor of 10, then the accuracy is increased by a factor of 100. So again, if I decrease h by a factor of 10, then I'm increasing the accuracy by a factor of 100. Or in other words, the error decreases by a factor of 100. However, the errors add up because at each step I'm picking up some error, and then at the next step I'm picking up some more error, and then all these errors are added up. So when I want to go from time 0 to time 1, then yes, the error is of order h squared. But if I add up all of those errors, so if I go from t0 up to a final time tn, which is a capital T here, then I'm making an error that is the sum of all the errors. So I'm picking up a factor of 1 over h here in the error estimate. So that 1 over h comes because I'm picking a factor of n by adding up n error terms. So in the end, the overall error is of order h for going from t0 to a final time tn or capital T. So in other words, this the Euler method overall, it has an error that's of order h. So it's linear in the time step. Okay, so if we want to implement the Euler method, we can start by calculating the result at n points. And by result, we mean numerical result or the numerical solution. So we calculate the numerical solution at n points with a step size h or delta t over an interval t0 to tn or capital T. We could specify this with any pair. For example, we can specify the interval delta t or capital T and n, and then from this we can calculate h or delta t, or we could specify n and the step size h, and from that we could calculate the interval, which is tn minus t0. Whichever way we do this, we would have a function for taking a single step of size h. That's convenient because then if we want to use another method for taking that step, such as Runge-Kutta or Hermite integration method and so on, only that part of the code needs to be changed. So the rest of the code can stay the same, and we can simply call a different function to take a different kind of step of time step. Okay, so to implement the numerical method, the Euler method, we do what's described here. So for an ODE with one variable of the form dy by dt equals f of y comma t, we need a code that will calculate the function f that specifies dy dt for a particular problem. So this could be a function such as double function of constant double y and constant double t, and then curly braces, and then we describe what that mathematical function does. Or it could be a function object if we want to store additional parameters. So we will see examples of this implementation very soon and in the labs. Thank you for watching.